Assalamualaikum to everyone and good day. So now I'm going to explain on the slope stability analysis for part A. So we will go through on the learning outcomes. So the learning outcomes for this week, week 9, at the end of this week, students should be able to explain the slope failure mechanism, analyze slope stability in terms of infinite and finite slope, Taylor's method and mass procedure for the total stress analysis. Okay, so first we look at the shear strength parameters for slope design. So this related with the shear strength that you have learned during your soil mechanics CEG561. So if you still remember the undrained or total stress analysis, the shear strength will be equal to Cu, and drain for effective stress analysis, the shear strength will be equal to sigma normal tangent phi. So remember, for drain or for effective must be have the this sign. Okay, in the stability of the cut or built slope, it depends largely on the changes in the pore pressure. So it may be rise pore water pressure after the construction, and they will gradually fall. So remember about the consolidation. So water will move out from the soil, and the most critical or lowest factor of safety, it may be expected to occur immediately after or during construction of an embankment. So after this, the soil will become stronger. So in contrast, the shear strength in the cutting diminishes with time, and so does the factor of safety. So it is necessary for us to consider both short term, which is at the end of the construction or immediately after construction, and for the long-term stability, which is a few few years after the construction. So the short term will be considered as a completely undrained, and the analysis is often referred as a total stress method, which is phi equals to 0 analysis. And for long-term problems, so we will take into account the effective stress analysis. Okay, next is about the slide creating new slip surfaces. Okay, so as usual, for clay, we have two types of clay, which is normally consolidated soil and over consolidated soil. So for normally consolidated soil, for undrained conditions, the peak strength will be lower than the critical strength. So the shear strength, the shear strength is equal to Cu. And for the drain conditions, the critical strength should be used as shear strength equals to sigma normal tangent phi. There is no Cu. And for heavily over-consolidated soil, so here is the equations that you can see here. Right, the slope, whether it's natural or artificial, man-made, so it divided into two, infinite slopes, which is example of long slope of the face of the mountain, and the second one is the finite slopes, which is finite slope which is limited in extent, and the example is the embankment and earth dam. Okay, for undrained infinite slope, so now we look at the infinite slope first. So as usual, we have undrained and drained conditions. So for the undrained finite slope, as you can see here, this is what we say forces, the forces elements that will occur in the infinite slope. Okay, so imagine this is a slope, okay, the infinite slope, and this is the slip plane, which is the plane, failure plane, okay, the failure plane. So the force that acting downwards due to gravity is the weight, okay, is the weight. And then the force, as you have learned during your secondary schools, right? In the physics, okay. So this force, which is perpendicular to the plane, is considered as N, normal, okay? Normal stress, and this N is equal to W cos beta C. Beta C is the slope angle of the slope. Okay, this is the angle slope. So here we have two components of forces, which is tangential force. Tangential force is the one that moving downwards, okay? Moving downwards to the slope, okay? Downwards, okay? Forcing down the slope, okay? And the second force is the shear resistance. Shear resistance is always going upward, which is contra with the tangential force, okay? Contra. So R is always going upward, is resist the slope from falling down, and the tangential force is the force that bring down the slope, okay, bring down the slope. So these forces, these three forces, normal reaction force, tangential force, and resistance, shear resistance force, is actually come from this forces element. And where is the weight of the soil is equal to gamma Lz. Gamma is the unit weight of the soil. L is the distance between these two lines, okay, in horizontal. Z is the depth, okay, Z is the depth of the soil. And because of the L is horizontal, and this slope is actually inclined, so L is equal to B cos beta. Okay, again, L is the horizontal, okay, the dimension, and because of the slope is inclined, width and width and beta angle, so L is equal to B, okay, B cos beta. Beta is the angle of the slope. So we can, what we have here is W equals to gamma Z, L is the B cos beta. Okay, and then N is equal to, because N is perpendicular to the plane, the slip plane, and it is actually N equals to W, okay, which is this one, W cos beta, okay, and T is equal to W, because T is here, the horizontal, the perpendicular to the N. T is perpendicular to the N force. So T equal to W sine beta. Right? And finally, R is the shear strength times B. Okay. Shear strength times B. And the shear strength for the undrained is equal to Cu. So actually R is equal to Cub. You still remember? Okay, so for this one, the undrained condition, we use effective. Okay, so when the pore water pressure is exists, so we have to consider drain condition. Okay, to make a shortcut So from the equation, so on, and finally we get the factor of safety for the drain condition. Okay, so gamma prime tangent phi prime over gamma tangent beta. Okay, or you can put it in pore pressure in the equation, which U equals to gamma water H cos power 2 of beta. So factor safety is equal to this equation, a little bit longer. Right, this is an example of drain conditions. Okay, such a drain condition. Okay, a granular soil has a saturated unit weight of 18 kilonewton per meter cube and an effective angle of shearing resistance of 30 degree. A slope is to be made of this material which is a granular soil. If the factor of safety is to be 1.25, determine the safe angle of the slope. 1. When the slope is dry or submerged. 2. If seepage occurs at and parallel to the surface of the slope. Okay, so in this case, the granular soil. So granular soil indirectly tells you that C is equal to 0. So you can just use the for dry or submerged. So for dry or submerged, that means the gamma prime and the gamma is equal. So when gamma prime is equal to gamma, so it is become 1. That's why F is equal to tangent phi prime over tangent beta. So the answer is 0.462 because the beta is 25 degree. Okay, so you get the beta is 25 degree from tangent beta equals to 0.462. And for the second one, because the seepage occurs at the parallel to the surface of the slope, so gamma prime is, as usual, gamma saturated minus gamma water. So 18 minus 9.81. And then times tangent phi prime. Okay, 0.5774. Divide by 18 unit weight, and times with factor of safety 1.25. And so you get 0.210. So your beta is equals to 12 degree. Okay. Right, next. Types of stability analysis procedures. Actually, we have two major classes. One is the mesh procedure. Basically, or normally, this mesh procedure is for undrained conditions. Method and then we have method of slices. Method of slices is more suitable for effective stress. So, but in certain condition, we also can use total stress analysis for method of slices. Okay, right. So we look at the total stress analysis, which is phi u equals to 0. First, we look at the homogeneous slopes. Okay, so imagine this is a slope. So actually, the total stress analysis it may be applied to the case of a newly cut or newly constructed slope in a fully saturated clay. So the critical circle, so in this case, our analysis would be the critical circle. So this is what we call critical circle. Okay, this critical circle. Theta, we normally consider the slip circle as a sector. As you can see here, there is a sector of AOB, and the slip surface is at the outline of AB. So your theta will be at AOB. W is the weight of the soil, so it's considered as the disturbing force. Okay, then D is the distance from the O, which we take a moment at O. So distance must be perpendicular to the force. The resistance force is along the arc line AB. So the distance from the resistance force is R. A is the radius, OB is the radius, and O to any line to the arc line is also considered as R. In cohesive saw, normally we have a tension crack. So to get the depth of the tension crack is equal to 2Cu over gamma, when K is equal to 1 because phi U is equal to 0. So the sector of AOB will reduce to sector AOC. So the resistance force now is along the arc length AC, and the area of the sector will be considered only the area that I lined the green color. Outline from C to B is no more considered, so just ignore the yellow section. Okay, and it's filled up with the water. So there is a PW. So the PW is equal to half gamma water times with Z power of Z. Sorry. So in the equation for factor safety, CUR square theta, which is the shear resistance moment, divided by disturbing moment, and you have to plus with PWYC, because pressure, the hydrostatic pressure or hydrostatic force inside the tension crack is considered as disturbing force. Okay, what is YC? YC is the distance from the center of the from the horizontal force, hydrostatic force, to the O. So don't worry, I will show you later the exercise, the example. Okay, this is the YC, right? YC is the distance from the PW, okay, PW to the O, right? And then if there is if there is a tension crack, okay, instead so your sector will reduce. Okay, instead of before existing of the tension crack, your sector will be AOB. Okay, AOB, and your theta is AOB. Okay, AOB. This is the whole angle is for theta. Okay, but when there is exist of tension crack, okay, you have to find out the Z naught. Z naught is the tension crack height. So your sector will be reduced to AOC. Okay, AOC. So BC is not considered. The arc line for CB is not considered. You only consider arc line from A to C. And your theta will be a new theta, which is AOC. B, okay, and then you have to consider PW if there is a water. If there is no water fill in the tension crack, so there is no PW. Okay, it's taken just now, yeah. For this example, we started with A, which is ignoring the tension crack. So the length AB is considered as the shear resistance force. Theta is considered for sector AOB, which is 84.06 degree. For these two cases, B and C, the theta is sector AOC, which is theta equals to 67.44 degree. And the area also decrease because the area is A, from here A, then C, only this area, So after after the tension crack, we not consider that area anymore. Okay, because the weight is considered before the tension crack. Okay, before the tension crack here. Okay, so 71.64 meters squared. So D also reduced because the weight is also reduced because the weight is always at the center of the section. Okay, so D is 5.86 meter, not meter square. C R squared theta over WD. No PW, so PW equals to 0, so still use the same equation. So your factor of safety 1.84 is increasing. Okay, then finally, when the tension crack is full of water, so when full of water, so you have to calculate PW. Okay, so PW half gamma water times Z naught squared, which is half times 9.81 times 4.32 squared. So PW is 91.54, and your YC is 6.7 plus 2/3. Okay, because this is actually a triangle. Okay, triangle. So 2/3 of the 4.32 Z naught. So you get YC is 9.58 meter. So the rest are the same, still the same. CUR squared theta, same with B. Theta is 67.44. R is 17.43. CU still the same, 40. Okay. D still the same, 5.86 meter. D is meter, not meter squared. Okay. Typo error here. Okay. D is 5.86 meter. Okay. W is still the same. Okay. But you have to plus with PWYC for this question. Okay. So finally you get factor of safety F is equal to 1.65. Okay, so that for homogeneous loop. And now for non-homogeneous loop, or what we can say is a multi-layer problem. Okay, multi-layer. Let's say the clay or the slope has a multi-layer. We have soil A at the top and soil B at the bottom. Okay, so the formula will be quite long, not so long, just a little bit long. Okay, so for when we have multi-layer, so we have two sectors. Okay, sector for layer 1 is BOD. Okay, BOD is the sector for layer A, the top layer. Sector for bottom layer is DOA or AOD. Okay, so theta, we also have two theta. If two layers, so we have two sectors, we have two thetas. If three layers, so we have three sectors and we have three thetas. Okay, so for the case, this case, two layers, so we have two sector. Top sector will be BOD. The second sector is DOA, and theta for the top layer is theta A. Theta from sector BOD, and theta B is from sector DOA. Okay, and if the CU is different, so we have CUA and CUB for layer B. Okay, same goes to unit weight. Okay, so for math procedures, it's given, the area is given, so quite easy for you. Okay, Actually, it's you have to calculate. There's a way to calculate the area, but we just give you the area. Okay, so the area for the top layer, which we consider for the sector BOD, is 65.943 meters squared, and the theta for the top layer is 25.32 degree, and D, because okay, when we have two layers, two sectors, two theta, so we have 2W. Okay, 2W. So the W for the layer A, the solid A, is WA, and W, the weight, because W is the force, right? The disturbing force, because we have disturbing force from the top layer and also disturbing force from the bottom layer. Okay, so WB okay, is for the bottom layer, and we have theta B, we have AB, which is 53.74 meters squared, and DB, okay, because the weight is a different position, location, so we have D, D, B, and DA. Okay, so this is R squared. It still use this formula CU R squared theta over WD. Okay, but so we factor R squared. So R squared, R is a 19.1 R squared times with CU R squared theta, right? So CU times theta. Okay, so CU A is 50. Okay, times with theta A is 25.32 plus CUB 30 times theta B 57.20 close bracket times pi over 180, because we convert from degree to the radian, and then divide by disturbing moment, which is W times with D, right? So WA is 65.94 times with 19 times with DA 9.79 plus with unit weight of B, layer B 53 18 unit weight for layer B. 53.74 is the area of layer B, and 2.85 is the D, distance force. Is from centroid distance of from O. So finally, factor safety is 1.29. Okay, last part for this week, okay, is the Taylor stability number method. Okay, we have four graphs, right? Four graphs, but this is the easiest graph. Okay, and we use equation NS equals to CU over F gamma H. So F, factor safety, is equals to CU over NS gamma H. D is a depth factor. Okay, D is a depth factor. So from this graph, this figure 9.18b is actually the easiest figure to use. Okay, I'll show you the example. Okay, this both figure 10.16 and figure 10.17 is from Taylor stability numbers by Taylor in 1937. A example here, a cutting in a cohesive soil has a slope angle of 35 degrees and a vertical height of 8 meters. So using Taylor stability method, determine the factor of safety against shear failure for the following cases. So the first one, A, CU is 40, gamma given 18 kN per meter cube, and D is large. When D is large, okay, D is large, 3, Okay, so when beta is less than 53, it will be 0.181. Okay, because D is infinity. Okay, D is infinity, so N is 0.181. So just use the equation, and S equals to Cu over F gamma H. So F is equal Cu over NS gamma H. So this is Cu 40, and S is 0.181 times with gamma, gamma is 18, times with H is 8 meter height. Okay. The second one B, when D is 1.5, okay, beta is equal to 35 degree, and phi u is equal to 0. Then from this figure, so n is 0.168. So how to get the n equal to 0.168? So we know that D is 1.5. So you can see here D equals to 1, D 1.2, this is D 1.5. This curve, okay, D 1.5, and the beta is 35 degrees. So 35 degrees is somewhere here, goes up until touch to the curve D equals to 1.5, and then go vertical to the y-axis, so somewhere here. So n is 0.168. So just substitute into the equation. Cu is equal to 40, and N is 0.168, gamma is 18, and H is the 8. So factor safety is equal to 1.65. Okay, lastly, okay, this is also Taylor stability number, but it is from Muni Budhu book. Muni Budhu use a little bit different figure to get the n value, because for this figure they use D naught and H naught. Okay, so H naught is the height of the embankment, the slope. D naught is the thickness of the slope layer below the inclined section. Okay, that is a D naught. So the equation a little bit different. Okay, how to get the factor safety is N naught times SU. SU is the Cu times over gamma H naught. So H naught is the height of the inclined section. D naught is the thickness below the inclined section of the slope. So you have to use this figure. Okay, so depends on the question, which figure that given. So you have to use a specific equation for the specific figure. Okay, I think that's all for week 9. So next week, see you again for method of slices for slope stability analysis. Thank you.